This video covers topic 8, section 5, which is titled margin of error. So in this lesson, students will be able to evaluate reports estimating population parameters, use multiple samples to make an inference about a population, and calculate the margin of error for quantitative or categorical data. So we're starting with looking at estimations of population parameters by finding sample statistics. So Seth selects a random sample of students from a local college and asks their year in college and how far the college is from their home in miles. So he's asking each student 2 different questions: what year they are in college and how far they live from the college. I'm sorry. And so we're asked 2 different questions. They want us to estimate the proportion of freshmen in the population, and they want us to use Seth's data to estimate the mean distance from home. So if we're looking at the proportion of freshmen in the population, all we really need to do is count how many freshmen there are. So in the sample, there are 1, 2, 3, 4 freshmen. So we're going to take 4 out of how many people is in the sample. So if I count how many people there are total, there's 20 people in the sample. So if I divide 4 by 20, that's 1/5, which is 0.2. Or I could write that as 20%. So based on Seth's sample, 0.2 or 20% of the college is freshmen. The next thing we're going to do is use Seth's data to estimate the mean distance from home. And so what that means is that we're going to take all of the numbers, because those represent their miles from home, and we're going to add them all together. So we're going to add each of those 20 data points together and see what the average distance from home is for this sample of students. So if I add up all those numbers, I get 2,017. Remember that there's still 20 people that he talked to, so we're dividing that by 20. So if I divide 2017 by 20, that gives me about 100.85, and this is miles from home. So the average distance from home that a student in this sample is 100.85. So the accuracy of estimates using sample statistics. So the accuracy of an estimate depends on the number of participants in the sample. So the number of participants in the sample and how well the sample represents the population. So it's not just that the bigger my sample is, the better my sample is, the more representative of the actual population is, the better my sample is. So for example, if I know what the actual percent of freshmen, sophomores, juniors, seniors are in the college, which is information that should be readily available, then I should make sure that my sample contains that same disbursement. Something similar with gender. So we can think about if I'm looking at a certain split for gender, I should make sure that my sample represents a mirror of that split. And so ultimately what's happening is that a larger sample will provide more accurate estimates than a smaller sample. So the larger the sample, the more accurate the sample is. If by chance the sample clusters away from the true mean, estimates will not be very accurate. So we are flipping a coin here, right? We're choosing a group of people that we hope best represents the population, and it could be that we just pick a bad sample. So that's why something called a sampling distribution is a better way to collect data. So this is collecting a variety of samples and then finding the averages of those samples. So the distribution of sample statistics, such as means or proportions from different samples of the same population. So the more samples that we take, the more accurate our results will become if we average those things together. So in example 2, Tia is contributing to the same project as Seth and has sampled a different groups of students. So Tia has the same questions. She's asking students, and we're going to look at first the proportion of freshmen in Tia's sample. So if I look at Tia's sample, which also has 20 people in it, she talked to 1, 2, 3, 4, 5, 6, 7, 8 freshmen. So she talked to 8 freshmen out of the 20 people she talked to. And so that's a 2/5. So she talked to double the amount of freshmen as Seth did, which means that her statistic is 0.4 or 40%. So B is saying, how can Seth and Tia determine whose result is a better representation of the population? And so ultimately, we're giving you the answer here because this is a new concept. So Tia and Seth decide to examine more samples, 50 total samples of 20 college students. So they take their 2 samples, right, and they do 48 more. So now they have 50 samples, all the same setup where they're talking to 20 students. And then they create a sampling distribution. So that means that they calculate out the proportion of freshmen in each of the 50 samples, and they use a histogram to represent that data. So they have 50 different proportions, and then that's represented in this graph. So by the empirical rule, one thing that we need to think about is where the majority of the data lies. So by the empirical rule, the majority of the data and we're going to look at specifically that 95% mark on the empirical rule, is between 2 standard deviations from the mean. So if we're looking at our graph where the mean should lie in the middle of this histogram. So the mean is somewhere between, in this section, because that's where the peak is of the histogram. So the mean is between 0.2 and 0.25, so somewhere in that range. And so thinking about that, if the mean is there, remember that the 2 standard deviations would mean that I'm looking at this chunk as the 95%, 2 standard deviations between the mean. So that's between 0.1 or 10% and 0.35 or 35%. So if we think about what we looked at in terms of their data, with their data, Seth's mean was here. So Seth's proportion was 0.2, and Tia's proportion was 0.4. If we look at on our graph, 0.4 technically doesn't even have any values because this goes from 0.35 to 0.39999, right? It's all the way up to 0.4. So looking at this, which of the 2 is closer to the mean based on this distribution? So they took 50 samples of 20 more students, and they found the proportion of freshmen. Seth's value is closer to that, where that true mean should lie, somewhere between 0.2 and 0.25. So that means that Seth's result is more likely to be accurate because it's closer to the mean of that sampling distribution. So now we're going to move on to looking at random numbers to help us mimic a study. So Gabriella wants proof that Alex's claim that he is a 75% free throw shooter. She observes Alex shoot 50 free throws, of which he makes 30. So that's a 60% success rate, not 75. But Alex points out that this is a reasonable result due to the natural variability and happens from sample to sample. So he's saying, yeah, my average is 75, like that was just a low one. And so what Gabriella does then is, so we're looking at random numbers to investigate his claim. So to see if it is actually a reasonable result, finding that 95% sample. So they used a random number generator to create a list of 50 random numbers ranging from 1 to 100. So 1 through 75 represent a successful free throw because he says that he makes 75%. So if I'm looking at numbers 1 through 75, 75% of those numbers are numbers 1 through 75. So anything that's 76 to 100, that represents missed shots. So if we look at these numbers, most of them are low. So I'm actually going to do this by counting. So we're just looking at how many of the numbers are successful free throws. So numbers 1 through 75 represent successful free throws. So we're counting those. Counted an extra 182 wasn't one. So that gives us 39 successful shots. So in this simulation, there were 39 successful shots out of a list of 50 random numbers. So 39 out of 50 is 0.78. So that's 78%. Okay, so in this simulation, if I assume that somebody makes 75% of their shots, 78% would be a reasonable outcome, right? They can make a little bit better than that. So then if we look at this sample distribution, so they did 50 more trials of the 50 shots to see what their number of successes were. And so what's happening here is that the average is that 0.75, right? So the middle is there at 0.75. So if we're looking at the range that contains 95%, so we're going to look for and select a range centered about the mean. And contains about 95%. And remember that since we have 50 trials, that's about 47. Okay, so what we're looking for is where can I find 47 results, and that's going to create my reasonable range. So if I look at this, so there were 16 that were 38 successful, there were 9 that were 37, and then if I make that go out a little bit more, there's 9 more. Then there were 12, then there were 8 here. This one has 11, this one has 10. So remember that I'm trying to figure out where can I get about 47 of these. So I'm looking for, if there's 50, I'm looking for to take off about 3, right? And so I should have done this from the outside. That would make this a little bit easier. But let's just continue from here. So this one has 3, this one has 5, this one has 4, this one has 1. And then this one has 5 again, 3, 2, 3. So if I want 47, then it looks like if I just cut off these last 2, right? If I look at that, that's 46. So if I take off the 3 and the 1 on either end, I could say that so that means that there's 46 between 31 and 43 successful shots. So 31, if we think about that, is 62%. And 43, if we think about that, is 86%. So what this shows us is that a true 75% free throw shooter would reasonably make between 62 and 86% of shots. So that means Alex percentage is probably not 75. He probably doesn't really make 75% of his shots because his free throw percentage in that one sample did not fit within that reasonable range. Okay, so this is looking at sets of data to find that reasonable range, that 2 standard deviations between the mean that contains 95% of the data values. So margin of error gives the maximum expected difference between the sample result and the population parameter. So we looked at, in the first half of this lesson, finding that 95% reasonable range. And ultimately, when we're looking at that visually, notice that it's really just cutting off the last 2 values if we have a histogram, right? So I'm ignoring the last 2 small peaks, and then the numbers that fit within that are what we call that 95% reasonable range. So when I don't have something like this, when I just have a set of data, I can find that margin of error in different ways. So it depends on what kind of data I am given. So quantitative data, remember, quantitative data is something that is numerical. So something that I can average, I can find the mean and standard deviation of, versus categorical data. So I have 2 different equations, and I have to use them depending on what type of data I have. So categorical data is literally just yes or no questions, that kind of thing, where I'm answering with a word. So that's the first question we have to ask ourselves, is what kind of data is this? One of the key clues as to what kind of data you have is if they give you a standard deviation, that means that it's quantitative. So they aren't gonna, you cannot find standard deviation if you have just a list of answers. So for example 4, we're going to calculate some of these margins of error. So the College Board recently reported that the mean score on the SAT math exam is 508 with a standard deviation of 121. Washington High believes that its seniors score considerably higher than the national average. So the schools randomly sampled scores from 200 seniors, finding a mean score of 550. Is Washington High correct in its belief? So let's talk about how we can answer this question. So if they are reasonable, then because they're saying that they're significantly better, that would mean that their results, their average, lies outside of that reasonable range for means. And so when we're finding this reasonable range, and I'm working with margin of error, that reasonable range is going to be between the mean of the data, so this is my actual mean score on the SAT, plus or minus the margin of error. So in our case, either one of these, right? So that's going to give us the reasonable range for the mean in this question. So what we're looking at is that we have a mean of all the people that took the SAT in whatever year this was collected for the math as a 508 score. The standard deviation is 121. And so what Washington High did is they took a sample of 200 seniors. So sample size, we're told, is the number n in this formula. And they found that their mean score, so we haven't used this yet, but we kind of talked about it. So because this is the sample, we're going to use X bar for that. So we talked about what X bar was when we introduced the notation for mean, but we were always talking about population mean, so we used mu. So X bar is 550. And so what we're doing is we're going to find this reasonable range by calculating the margin of error. So I talked about already that if standard deviation is included in the problem, then you're going to use the formula with standard deviation in it. If it doesn't say anything about standard deviation, that means that you have categorical data, and you're going to use the formula for that margin of error. So since I have a standard deviation, that tells me that I have quantitative data. But I can think about that as if I'm finding a score, right? A score is numerical. So the margin of error is equal to 2 times the standard deviation divided by the square root of the sample size. So 2 times 121 divided by the square root of 200. And so if I calculate that out, 2 times 121 divided by the square root of 200, that gives me a margin of error of about 17.1. So what I want to look at then is what is the reasonable range of means. So reasonable values would be the population mean, which is 508, plus and minus my margin of error, which is 17.1. So that means I'm going to take 508 minus 17.1, which is, oh, I use 17, well, whatever, which is 490.9, and then 508 plus 17.1, which is 525.1. Okay, so that means that a reasonable set of values would be between those two numbers. So the reasonable would be between 490.9 and 525.1. Since this number, 550, so since 550 is greater than the reasonable range of means, Washington High School is correct that their seniors did much better. So we had to calculate the margin of error for quantitative data, then add and subtract that number from the true mean of the population, so what College Board said that the mean of that year's data was, and then compare, is Washington's score between those two numbers, or is it outside of those numbers? Did they actually perform better than where the true average lies? So remember, this reasonable range means that an average that is close to that would be land anywhere between 490 and 525, that would be a true statement that they're close within the average. For part B, we have a random sample of Washington High seniors that reveals that 40% of them plan to take the SAT this year. So this is a yes or no question. Do you plan on taking the SAT? Yes or no? So we're using the margin of error to predict the actual proportion of seniors planning to take the exam. So remember that since they're asking us whether we plan to take, that's a yes or no question. So this is categorical. Again, there's no mention of standard deviation. That's another hint that we're looking at categorical data. So all that we really need to know for this is the sample size. So it's a sample of 100. So N is 100 for this situation. They're giving us their data. So the 40% of them plan to take the SAT. This is a proportion. So this is P is 40%. And so what we're going to look at is what is the true proportion. So if I add and subtract the margin of error, that'll give me a better indicator as to where the true population's proportion lies. So since we're looking at a categorical question, we're going to use the other formula, which is just 1 over the square root of n. So our sample size is 100. So the margin of error is 1 over the square root of 100, which is 1/10 or 0.1. Since this is given to us as a percent, let's say that that is 10% then. Okay. So the same way that we did with the last problem, we're going to add and subtract this value from the value that we were given as the representation of the true proportion. So the true proportion it will be between that 40% plus or minus that 10%, which is 40 minus 10% is 30%, and 40 plus 10% is 50%. So the true population should be between 30% and 50%. Okay, so in example A, a poll reports that 25% of voters in the city want a stop sign placed at a particular intersection. The poll reports a margin of error of plus or minus 3%. Estimate the number of voters in the poll. So they're giving us the proportion, which is 25%, right? So the proportion is 25%. That was the result of the poll. And they also give us the margin of errors. The margin of error is plus or minus 3%. So that's about 0.03. So the margin of error is 0.03. Since this is a yes or no question, right, this is categorical. So do you want something? So this again is a categorical question variable. So we're going to use that same margin of error formula again. So the margin of error is equal to 1 over the square root of the number of voters in this case. So we know that M is 0.03, so we're going to plug in 0.03 for M and then use that to solve for N. So 0.03 is about equal to 1 over the square root of N. Since I have one side as a fraction, I want to think about this other side as a fraction too. So if I were to cross multiply this, that'll give me 0.03 times the square root of N is equal to 1 times 1, so just 1. So then I would have to divide both sides by 0.03. So the square root of N is about 33.3. That's really repeating. So then to get N by itself, I would have to square both sides. So N is about, if I square this, I get a bunch of 1s. So that means that about 1,111 voters participated in the poll.